Hi everyone, Mrs. H again, trying to go through some additional lessons on our Ka acid-base lessons, kind of applying some of that areo, atom, resonance, induction, and orbitals, the areo system, in determining strengths of acids, and just really comparing the ability to stabilize their conjugate base. We can also apply those same rules or same ideas of areo into predicting the side of any equation that would be favored at an equilibrium. In a previous section, we talked about a quantitative way to determine the equilibrium push, and that was using the pKa chart. And we said that when comparing the acids, and again, noticing that we have two acids in this acid-base equilibrium, HA or HB, whatever that might be, and we looked up the pKa values, and we said, let's suppose we had a pKa value here of approximately 30, and this one was approximately 50. Those are larger numbers, so these would be weak acids. But definitely we saw that the equilibrium would favor the production of the weaker side. So the equilibrium lies on the side of the weaker acid. And so we did that using pKa values. The higher pKa will be favored since that's the weaker acid. And then you can think of the relative stability of the bases, their conjugate base, B negative or A negative, knowing that the more stable the conjugate base, the more strong the acid is. So this must be a more stable conjugate base, less stable conjugate base. Because, let me just write CB for conjugate base. We know that the less stable conjugate base would have the weaker acid. So what about applying these areo and kind of predicting equilibrium sides? And let's just try to do these without a pKa chart and just kind of go through the logic of areo. So I'm going to determine which side of the equilibrium is being favored. And first of all, let's hook together the conjugate pairs so I can identify the two acids. So what are the conjugate pairs? We're finding the acids. So here I have a structure that has an oxygen. I'm just going to point out really something we should see. This oxygen forms conjugate pairs, and then notice here this is a sulfur, and those are going to be conjugate pairs. Everything else in this chemistry is exactly the same. So this cyclopentane, see how it has a five-membered group? I'm attaching conjugate pairs. The one with more hydrogen is always the acid, so this is its conjugate base. And if I think here between this and this, those are two conjugate pairs. They only differ by the presence or absence of a hydrogen. This would be the acid. It's actually the conjugate because it's on the right side. And then this, of course, would be behaving as a base. So we find the acids. And now without a pKa chart, I would have just said, go to the chart and find their Ka values or their pKa values and decide which one is the weaker, knowing that that would be the side being favored. But we don't have a pKa chart. So let's use and kind of influence areo to decide which side is now going to be favored. And it has to do with the ability to stabilize the negative charge. So what did we say the difference was? Well, here's a base. The conjugate base here has a negative charge on a nitrogen that is going to be resonance stabilized. Notice it's next to a sulfur that's involved in a pi bond. So this is resonance stabilized. And the atom it will be stabilized with is a sulfur. On this side, this is a conjugate base, and the atom that it's on is a nitrogen. So in terms of the atom, that's the same thing, and they're both attached to an N. In terms of resonance, that's the same, right? Because we can see the electron, we can see that it will be resonance stabilized for both of those. So yes, that's really the same. They're both resonance stabilized. So that's not really a deciding factor. So what about the induction effect? Thinking about a Are there any electron withdrawing groups? Are the orbitals anything to consider? And as I realized about resonance in atom, I don't really need to go any further because resonance stabilization across a larger atom will allow me to make my decision of what's the more stable conjugate base. Sulfur is the larger atom compared to oxygen. So this is also resonance stabilized, but it's being stabilized by a smaller oxygen atom as compared to the sulfur, which is the larger atom. So yes, they're both attached to nitrogen. Yes, they both exhibit resonance. Really, induction and orbitals don't play a role here. So I have to decide between the sulfur and oxygen, who's going to be better at stabilizing the delocalized electrons. And that means that the sulfur wins, right? It's the larger atom, a greater surface area is going to help stabilize the negative charge better. So that means this is a more stable base, meaning that its acid over here is a stronger acid, which now helps us remember that the stronger acid always pushes towards the weaker side. So this equilibrium is going to be lying to the left, which has the weaker acid. And I did this without using a pKa chart. So we went through a series of steps without a chart and just kind of talked through how we could decide which one would be a more stable configuration. We found the two bases. And we did so really by just hooking together the conjugate pairs. The base has one less hydrogen. And we said since they're both on a nitrogen atom, we had to decide based on resonance, even though they're both resonance stabilized. We said sulfur beats oxygen in this resonance stabilized structure because it is the larger atom, and a larger surface area is going to help stabilize that delocalized set of electrons better. And therefore, since this is a more stabilized base, it came from the parent who was a stronger acid, and just kind of applying the more stabilized base is going to have the equilibrium lie on the same side. This equilibrium is going to be favoring the left side of the double arrow. So to kind of think about that, you'd have an arrow distribution showing the left side is dominating. We can apply the Areo system to predict the position of equilibrium for each of the following reactions. And I just pulled one from your homework. So what I've done is kind of set up this is an alkane. This is sp3 hybridized. And this is just the presence or absence of its hydrogen. So just to kind of think about conjugate pairs, those two are called conjugates. The acid is the one with more hydrogen on it, and so this, therefore, is its conjugate base. That makes these two conjugate pairs. That means the one with more proton is the acid, and over here is its conjugate base. Look and find those bases and see, which one is better stabilizing the negative charge. Areo. The atom that the negative charge is on. In the first structure, the atom here is on a carbon. Over here, the negative charge is on a nitrogen. Right here we can stop, right? There is no resonance, there is no induction, there is no orbitals to consider, so I'm looking at the very first criteria, the atom. The more stabilized will be the more electronegative element. This is the more stabilized base. The negative charge is being distributed over the more electronegative element. The more stabilized base told us that its conjugate acid was stronger. And therefore this acid must be the weaker acid. We know that we're going to favor the side that's showing us the more stabilized base, that we're showing the side that is producing the weaker acid. And I just said that same thing two different ways. Stabilized base is the side that's favored. So clearly we see that this equilibrium will be favoring the right side, so the equilibrium arrow shows more product than reactant at equilibrium. Same idea, just kind of applying what we look at in terms of equilibrium to REO and deciding which one would be the more highly stabilized conjugate base. Another application of REO is choosing the appropriate reagent for a proton transfer. For example, we might be asked something like, is water a suitable reagent for deprotonating the acetate ion? The acetate ion is the resulting conjugate base from acetic acid, COOH. And so what we're really asking ourselves is to consider the Bronsted-Lowry acid base and think this through. Is this going to work? So we have a water molecule, HOH, and it's going to be in dynamic equilibrium with the acetate ion. And there's the negative charge. So remember, Bronsted-Lowry says a proton transfer will occur. And that's our whole chapter, right? Thus far till we get to Lewis. But proton transfer always involves two arrows, right? The electron-rich area on the base is going to reach out for the proton on the acid. And when it does so, this bond collapses and we form conjugate pairs. The conjugate base of water is hydroxide. The conjugate acid of the acetate ion is acetic acid. So here we've just protonated the acid. There's that proton on the oxygen, right? So we've really just set up conjugate pairs. Will this reaction occur? And if it does, that means that the base that's produced is a very stabilized base. Now, I forgot the negative sign. There we go. Let's compare OH negative to the base of the acetate, right? Those are the two bases in our structure. REO, A-R-I-O. The very first letter is A for atom. The negative charge on both of these bases is on the same atom. It's on oxygen. So that's really not helpful. Let's go to the next letter, R, REO. Resonance. Which one of those is resonance stabilized? Well, clearly you can see the negative charge here on this oxygen has the ability to be resonance stabilized because the carbon next door is involved in a pi bond. So yes, this is resonance stabilized, whereas this is not resonance stabilized. So this must be the more stable base. Which means its parent acid was stronger. And both of those decisions let us realize that the equilibrium always pushes towards the weaker side. The equilibrium always pushes towards the more stabilized base. So this equilibrium is lying to the left. Is water a suitable reagent for deprotonating the acetate ion? And the answer is no, because this reaction did not proceed in the forward direction with any kind of certainty. We're just saying, no, this really didn't happen. So the resonance structure of the acetate ion showed that it was the more stable configuration. And when we realized that, the left side of the arrow is favored, and golly no, we don't have any of that forward direction. So the equilibrium favors left side. If we wanted to deprotonate the water, that is not the correct selection of reagent. Is this an appropriate reagent selection? All right, so here we have, let's say we're going to take some water, and I want to protonate this molecule that contains nitrogen, and you see how there's a negative charge? So to have a negative charge, it actually has two sets of electrons, right? Nitrogen needs 3 bonds and 1 lone pair. So if it's negatively charged, it has 2 sets of dots and 2 bonds. It is 1 bond deficient. So when this occurs, this negative region on the nitrogen is going to reach out for the hydrogen, and it will collapse the bond onto the oxygen. So we have our conjugate base of water, hydroxide, and we would have the conjugate acid form, because I'm getting emails. And so there's the acid-base conjugate pairs, 2 electrons for this proton transfer. What we're really being asked is, does this reaction proceed to the right? Is this an appropriate reagent? Means we're going to be favoring the right side. Proton transfers are acid-base chemistry. They involve 2 reaction mechanism arrows. This is a base, and this is a base. Ario. Which one of those is stabilizing the negative charge better? Right off the first letter, it says atom. This is being stabilized by a nitrogen atom, and this is being stabilized by an oxygen atom. They are different from each other, so I can make a decision right with the very first letter of ario. I don't even need to progress, because oxygen is the more electronegative element. This is the more stabilized structure. And therefore, this is the, just thinking about the favoring side, we know that it will favor the more stabilized conjugate base. Think about what I just said. This is the stronger acid because it produces a very stabilized conjugate base, compared to this, which is a weaker acid, and the equilibrium lies on the weaker acid side. So definitely we could see this equilibrium favoring the right side. It's favoring the more stabilized conjugate base. It's favoring the weaker acid. And so, yes, this is a reagent that would work great in protonating that base, because I'm actually seeing a reaction proceed in the forward direction. Another application would be selecting a reagent to protonate the following molecule. So what I want to do is kind of go from this base and produce its conjugate acid. So I want to add that proton back on. Alrighty. So I'm really asking you, what can I place here as an acid that when it forms its conjugate base, on this side we end up with conjugate pairs. This conjugate base has to be very stable. All right, just kind of thinking that through. Well, this is the game. I just put a little snapshot of the pKa chart, because in order to select a reagent, you got to use your pKa chart to even know, what are some choices. And I'm just looking down here. I know I need an acid, so I know I'm going to be looking in the left column, because this says I want to protonate. To protonate, that has to be the base. So these electrons here are looking to attach a hydrogen back. So I know that you're going to be identified as a base. So I got to look down the left column on my pKa chart and find some acids. And I have to look at these and decide which one's going to be better. Do I want to look above acetylene, C2H2, or do I want to look below acetylene for an acid that will protonate? Well, the answer says we want to make sure that we're producing an acid that's weaker than what we started with. And so I want to look above acetylene. And let's just go like one above, shall we? Let's say I'm going to put in a reagent that is a ketone. And next door to it here is this hydrogen. That's the one I'm selecting right here. That would be a reagent. It's a ketone because this is a carbonyl attached to two other carbons. It's a functional group of a ketone. I could pick the alcohol that's tertiary. I could pick the alcohol that's primary. This carbon is attached to three other carbons, tertiary alcohol. This is a primary alcohol. It's attached to just one other. Here's just a simple water molecule. Any of those work because when I have the acid, it's pKa of 19.2. And I compare that to the conjugate acid of acetylene, which is 25. I am pushing towards a weaker acid. I am pushing towards a more stabilized conjugate base because this happens to be resonance stabilized. When I remove this proton, I come up with a conjugate base that will be resonance stabilized, and that's also favoring the right side of the equation. So any acid that has a pKa showing a stronger acid, meaning a smaller number, will be a successful reagent in putting the proton back on. And so I just used a pKa chart. What would not work is picking an acid that has a, that's too weak to be able to protonate that acetylene. I'm going to talk a little bit about some topics here at the end of our chapter and really kind of laying some foundational work for mechanism. The first of these topics, I'm going to talk about leveling effects, solvation effects, counter ions, which I call spectators, and a brief little talk about Lewis acids and bases to round out our chapter. The first of the effects is we start selecting reagents and the medium to run equations in will be a leveling effect. Now let's decide what that means. It says to define the term leveling effect. It's an effect that prevents the use of bases that are stronger than the conjugate base of the solvent employed. Okay, so let's think about what I just said. To do Bronsted-Lowry acid-base theory, we need a solvent. Even if I were to just draw a simple acid-base theory where we get a H3O plus and a Cl negative. In this example, we need some sort of medium for ions to swim around in. In that classic example of acid-base chemistry, water is the solvent. See, if I were running these in a gaseous medium or some sort of solid medium, molecules don't have the ability to ionize and exchange partners. They have to have some sort of solvent, some medium to allow the kinetic motion of the molecules to collide and for bonds to break. We have to have a medium for the solution to allow proton transfer. So that's what a solvent is for. It's the medium that allows molecules to collide with one another and to break bonds and to reform new bonds. Has to occur in some sort of medium. Typically, a very common medium is a water for acid-base chemistry. But sometimes water itself isn't a good choice, and let's talk about why when we discuss leveling effect. The key here of selecting a solvent in the lab to run your acid-base reactions, the solvent should be able to surround the reactants, kind of help to stabilize them based on polarity and facilitate their collisions, but it itself should not react. It has to not participate and consume the acid or base in reaction. Because water really is an acid or a base, that word we learned in Gen Chem was amphoteric. It can act as an acid or a base, a proton donor, proton acceptor. It has a leveling effect on very strong acids and strong bases. Acids stronger than hydronium cannot be used in a water medium. Here's hydronium on your pKa chart. If I'm using an acid that's stronger than hydronium, it actually consumes that acid and takes it out of the reaction. Bases that are stronger than hydroxide. So let's find hydroxide on our pKa chart. And it says, here's hydroxide, for example, and these are the base side. And bases actually increase in strength as you go down. Anything below this is a stronger base. Base is stronger than hydroxide, cannot be used in a water medium for the solvent. And I'd like to describe why in the next few slides. So selection of the solvent is critically important. And that's what we refer to as the leveling effect. We want to be sure we're selecting a solvent that actually promotes the reactions instead of destroys the reaction. Let's dive into that topic. Appropriate use of water as a solvent when the base is not stronger than hydroxide. All right, so here we have the acetate ion. This is a conjugate base of the acid acetic acid. These two are referred to as conjugate pairs in the Bronsted-Lowry theory. Water, H2O, has a conjugate of hydroxide. Those two are conjugate pairs. When we identify the acids, H2O is acting as an acid, and acetic acid, COOH, is acting as the acid. I've identified the acids in both sides. And I pull out the pKa chart, and the pKa chart says the stronger acid is acetic acid. It's going to stabilize its conjugate base, and clearly we can see that the base is stabilized through the resonance of that oxygen, even though we have the same atom stabilizing, right? Stabilized by oxygen in both of these bases. The resonance structure makes this a more stable conjugate base. And clearly we see that the equilibrium lies on the weaker The equilibrium lies on the more stabilized base side, and that's the left side of this equation. So the left is being favored. What that means is that when I put water into this solution, I am not destroying the acetate. And that's important because let's say I want to do a next step. I want to actually have acetate be protonated by something else. I need a solvent to do that. I don't want to put water in as the solvent and have it destroy the acetate by making the reaction push right and taking it out of solution. I can then take the acetate base and select an acid, not water, but an appropriate acid as we had done in the last section, and actually produce conjugate pairs. Water can act as the medium, the solvent, and not participate in the acid-base chemistry because it will not destroy the acetate ion. The solvent must keep the equilibrium on the left side. If you add a solvent and it pushes the equilibrium to the right side, you destroy the original molecule, and the reaction that you want to have happen will not proceed. Let's take that example. Here we have a very strong acid. It's sulfuric acid, pKa of -9. Isn't that at the very top of your chart? So if this is an acid, water would be acting as the base, producing the conjugate acid. Whoops, I'm sorry, that's the conjugate base. These two are conjugates. And the conjugate acid of hydronium. So when I find those two acids, I'm comparing hydronium, pKa of -1.7, and sulfuric acid with its pKa published at -9. Clearly you see that the equilibrium is going to be pushing to the right. It's going to favor the weaker acid. It's going to favor the more stabilized conjugate base. Notice this conjugate base, when I compare water, this will have resonance ability to delocalize actually across two different pi bonds, so a very stabilized conjugate base. So what have we done? If my goal was to have sulfuric acid react with something, let's say I want to have it react with ammonia. Let's actually do some chemistry where I want to add an acid and a base. And I need something for the molecules to be in. I need a solvent. If I put that sulfuric acid into water, I've destroyed it because it gets consumed when the equilibrium favors the right side. So this is no longer there. What's in solution is its conjugate base. And therefore, I don't really have the starting material to react with the next reagent. So when I select a solvent, I want to consider the strength of that solvent to make sure it doesn't consume the acid or the base. I want it to keep the equilibrium to the left so that that molecule is not destroyed by the presence of the solvent. And you can consider these as well, bases. Any base stronger than hydroxide cannot be used in water because, for example, we wouldn't be able to perform the following acid-base reaction. So for instance, if I had, here's an acid, this is a base, we formed a conjugate base and a conjugate acid. That's the chemistry I want to have happen, all right? So let's suppose I place, this particular base in a water solvent. If I did this, N going off in both directions, here's the negative charge, and I place water as the solvent, the acid-base chemistry occurs to create conjugate pairs. We would produce the conjugate here with the hydrogen on it, and again a lone set of dots, and the conjugate base over here of OH negative. So I would be comparing the stability of the base that has nitrogen stabilizing the negative charge, and I would compare it over here to this base which has oxygen stabilizing the negative charge. Since oxygen is more electronegative than nitrogen, these are the two bases, the more stabilized structure, stabilized. I don't think I spelled that right. May I try again? There we go. The more stabilized base is going to say we're favoring the right side of this equilibrium. And therefore, if I favor the right side, I've destroyed this base, and in its place, we have hydroxide. Well, that's no good. If I had a water solvent, I would not be able to carry out this reaction because this would no longer be present. It would have been exchanged with hydroxide, and I don't have any of the desired outcome on the right-hand side. So water cannot be used as the solvent in this particular example because it destroyed the base and replaced it with the hydroxide polyatomic ion. And so you'll kind of read through and say, we need to show a better choice, working with this particular substance. You can see that we're going to be favoring the left side of this equilibrium based on the pKa's or the stability of, the hydroxide ion there. And so we'd destroy it. And therefore, this reaction wouldn't occur. What could we use in its place? Anything that would have an opportunity to set up a solvent that would not destroy. So that would be anything stronger than hydroxide. Oftentimes we use liquid ammonia with amide. So the leveling effect kind of describes for us the careful selection of a solvent as to not destroy one of the acids or bases and take it out of the reaction. Because they're so similar, areo cannot really be used to explain the pKa difference between the following ethanol and tert butanol. And this leads us to talk about a second effect, The first being leveling, the second being solvating. Here we have tert butanol. 1, 2, 3, 4 carbons in that structure. That's the prefix but. And I can also see this alcohol functional group with the OL ending. And we call this a tertiary alcohol. The tertiary alcohol means that the carbon bonded to the functional group of OH, that's this carbon, is bonded to 3 other carbons. This carbon attached to the alcohol functional group is attached to just one other carbon. It's called a primary alcohol. If we went through areo, why do we see a difference in the acidity when they're bonded to the same atom? None of them exhibit resonance. There are no inductive effects, and they're in the exact same orbital. You see how close areo is to both of these? So what can we do to explain what makes one more acidic than the other? And clearly by looking at the proton here, this is the more acidic proton. But why? And again, the answer comes back to the solvent. The ability of the solvent to stabilize the conjugate base's negative charge helps to create a stronger acid. Look at this diagram with me. This is our tert butoxide, right? This is the negative ion, the conjugate base of that alcohol we saw on the previous slide. This is the conjugate base we saw of the primary alcohol. Notice this big area over here presents a very bulky, sterically hindered area. I'm getting all kinds of emails. This here is a big, bulky area. So really the only interaction that this negative ion has, this is the oxygen part, right? So that's all of the negative ion. The only interaction that this solvent might have, and if it's water, for example, we'd want to align the hydrogens there to help stabilize the charge, right? Hydrogens are partial positive, so water would be trying to align itself to place the hydrogens next to it just to help stabilize with these hydrogen bonds. Now, it's not doing so very well because this big bulky area of this tert butyl, big bulky base area, you'll hear me say that a lot. This is a big, bulky base. It has a steric hindrance because of its, lots of carbon in that area. And it makes the water molecules very difficult to have access to this oxygen to help stabilize it. Whereas if I have kind of a less hindered area, the solvent has a greater surface area available to it to help distribute that electron charge. And again, especially if this is water as the solvent, which it probably would be here, you're setting up these little attractions called hydrogen bonds with a greater surface area that water can set up the stability. This ends up to be a more stable negative charge. And therefore, the solvent itself has the ability to stabilize the negative charge, and it's not areo with an S for solvent. So you have to kind of consider that when everything else has failed, what is it in? Is it in a molecule such as a water solvent that help to distribute these ion dipole attractions? And if so, you're going to see this more stable structure being the least sterically hindered structure. So for example, which one of these is the more acidic compound? You have a carbon to carbon OH and just plain HOH. And I didn't mean to make that linear. It's a zigzag as well. But again, notice this chain here. This chain is kind of a non-polar area. It's the hydrocarbon chain, which kind of creates, a bulky area, whereas this guy has no steric hindrance at all, making this proton more acidic than this proton. the less sterically hindered it is, the more acidic, the more stabilized the molecule becomes. So I'll just say less steric hindrance to allow stabilization by the solvent. We selected water as being more acidic. Counter ions, I often call those spectator ions. These are ions that are necessary in our chemical acid-base reactions just to keep the electrical charge neutral. Spectator ions do not participate. They are simply there to keep the electrical charge. So here I see a sodium amide. Really, you can see that as two separate ions, a sodium and an amide. And of course, here's your water molecule. On this side, you have ammonia. And on the other side here, you have sodium hydroxide. I just want you to notice what's happened with sodium. Sodium is aligning itself first near this amide. And really just think of these as two separate entities. One is called a cation, a spectator. The other is called an anion. They're held together by electrostatic charge. So it's there to stabilize the negative charge, right? I can't just go to the shelf and pull off a negative ion. It has to have a first name. But as this proton is then transferred and this bond collapses and we form hydroxide, where does the sodium then migrate to? Well, based on the electron distribution, this sodium ion is now going to migrate next to the hydroxide ion just to help stabilize its charge, create a neutral compound overall, but it did not participate. So those are called counter ions. They simply counter the balance of charge. You might hear them called spectator ions. They're only there to counter the charge. We do not necessarily have to write them in the reaction. So if you see some example of like lithium, which is plus, and acetate. Acetate would be a carbonyl group leading out to the oxygen. That would be an example of a lithium. And then this would be its conjugate, this base part would be the acetate. And if you see that react with water, the acid-base proton would transfer, so you'd see the oxygen reach out for this proton and the bond collapse. On the opposite side now, you'd form the conjugate acid of acetate, which is acetic acid. Oops. That's all one big bond, so that kind of separated for whatever reason when I drew it. And then over here, you'd have a protonated, deprotonated water, and then of course the sodium would just migrate over there. So the lithium would just migrate over there, just some kind of usually an alkali metal that's just there to stabilize charge. In this case, lithium ion is called a counter ion, or it's called a spectator ion. And our chapter is going to wrap up sharing a third working definition of acid-base theory. The common one is called the Arrhenius definition. Arrhenius says acid starts with an H, bases end with an OH. We talked about at great length Bronsted-Lowry being proton transfer. Acids donate protons, bases accept protons. And the third working definition we should be familiar with is the Lewis acid and the Lewis base. This is the same gentleman that gave us Lewis dot structures, right? So that's a Lewis dot structure for chlorine. These are the Lewis acid base definitions. A Lewis acid accepts a pair of electrons. A Lewis base donates a pair of electrons. Under the Bronsted-Lowry definition, anything that is a Bronsted-Lowry acid is still a Lewis acid. Anything that was a Bronsted-Lowry base is still a Lewis base. It fits both definitions. For example, in this definition, water is acting as a base HCl is acting as an acid because we've had a proton be transferred. This here, HCl, was a proton donor. Over here, this was a proton acceptor. That's the Bronsted-Lowry acid-base theory. And on the opposite side, we have conjugates. Now keep in mind, Bronsted-Lowry is the only definition that has conjugate pairs. Arrhenius, no. Lewis, no. Bronsted-Lowry, yes. Conjugate pairs. This is the species that forms on the right side. The conjugate acid forms from the base. The conjugate base forms from the original acid. With the Lewis theory, we're not looking at the right side. We're only identifying acid base here. Now look at how we could also envision this. The oxygen is donating a pair of electrons. It is an electron donor, electron pair donor, as it forms a bond with the hydrogen. That's the electrons that were donated to make a shared pair. On the opposite side, the acid accepts an electron pair. The hydrogen accepted the electron pair as it formed the bond, resulting in the transfer over to the hydronium. So they're still going to work. Bronsted-Lowry acid base are the same as Lewis acid and base. But now let's take a look at what makes Lewis acid and base an even broader definition than Bronsted-Lowry. And really, this is the classic definition where you look more of a combination reaction where you have a single product on the right-hand side. That really is unique or key for the Lewis theory. Arrhenius and Bronsted-Lowry working definitions always had A plus B gives me C plus D. You'd have two products on the right-hand side. The Lewis theory allows us to look at more of a combination or a synthesis pattern of reaction where a single product is formed. Here we have an electron-rich area on the water, and here we have an electron-deficient area on the boron. And again, that's really just inductive forces here pulling the electron density away from boron, making it a positive charge. So as these electrons reach out for this positive area on the boron, a bond forms. Because the electron pair donor came from water, water is acting as a Lewis base. Because the boron accepted the pair of electrons, BF3 is acting as the acid. And you produce a single product where a new bond has formed between the electronegative rich oxygen and the electron deficient boron. And one product formed. Identify the acid and base in the Lewis theory with this reaction. Remember, you can detect Lewis acid-base theory because it forms a single product. There are no conjugate pairs in the Lewis theory. So that means one on the left is the acid, one is on the right. One is on the left as an acid, the other must be the base. Look for the electron-rich area on the oxygen. Look for this electron-deficient area on the boron. I can see a bond forming between the oxygen and the boron, and that's this bond right here. It results in a positive charge on the oxygen. The formal charge is +1 on the oxygen. The formal charge on boron becomes a -1. But a new bond did indeed form. This right here was the electron pair donor. That means this was the base. And this right here was the electron pair acceptor, meaning this one acted as the acid. So the acid plus base combined to form a single product in the Lewis acid-base theory. You have a couple more to kind of look at on your homework, your skill builders. I want you to find the electron deficient area on the aluminum, and you can see the electron rich area on the oxygen. And then just follow the electron flow. You see how there's a new bond between the oxygen and aluminum? That tells us exactly that this was the electron pair donor, making this the base. Aluminum was the electron pair acceptor, making this the acid. Here we have a ketone, and notice the ketone here has the oxygen, even though they're not drawn, we see oxygen up here. And then we have a positive charge on hydronium. And what do we see? On the right side, well, I see conjugate pairs. I don't see a single product like I did up here. A single product is only unique to the Lewis, right? This is unique to Lewis. But when I see conjugates, I notice that I can see two species on the right-hand side. I have conjugate pairs. I'm going to fall back to my Bronsted-Lowry and say conjugates differ only by the absence or presence of a hydrogen, and the one with more hydrogen is always the acid. So that ketone must be the base. This hydronium is acting as an acid, forming its conjugate base. And so thinking about the actual chemistry, you can see the oxygen reaching out for one of these equivalent hydrogen and the bond collapsing, and you form the conjugate pairs. So you could use either Bronsted-Lowry or Lewis, whatever you're more comfortable in, if you see conjugate pairs forming. If you see a single product form, that's unique to the Lewis theory as well. Oh my goodness, we have done it. We have looked at all of the content for Chapter 3. You have done a brilliant job. You need a rest. I need a rest. When ready, I'll challenge you to start your next Orion, your Wiley Skills Builder, and please prepare for your chapter quiz. Come back when ready.